Hello there. Today we're going to talk about drawing Lewis structures. This is part one of two parts. Lewis structures are drawn for molecules. Those are covalent compounds where the electrons are being shared. So here we go. Molecules share their valence electrons. The arrangement of the atom is important, or excuse me, the atom's structure of the molecule is important, so that we can understand their chemical properties and their physical properties. Like boiling point, physical property, melting point, polarity, solubility, how it will dissolve in water, and reactivity, chemical property, how it will react with other elements. All right, there are steps that we're going to do for drawing these Lewis structures. Any picture that's drawn, you don't have to draw unless I specifically tell you to. Okay, so count the number of valence electrons. If it's a polyatomic ion, then we have to worry about the charge. And so what polyatomic ions have is that they've gained electrons. So right here you see sulfate has a 2- charge. This means that it's gained 2 electrons, and the electrons outnumber the protons. For positively charged polyatomic ions like ammonium, what's happened is this ammonium has lost electrons, and now it's positive. The protons outnumber the electrons, so we subtract electrons from the total. When you're looking at valence electrons, you have to look at the group number instead of like writing the electron configuration and figuring out the number of valence. It's easiest to just look at which group it's in, and that's only for the A elements. So these right here. All right, next step. Figure out which atom you're going to put in the middle. Be based on electronegativity. Most of the time it's written in that order where we write the least electronegative atom first, and you kind of have to make sense of what you have. For example, I have CF4. Makes sense that I have 1 carbon and 4 fluorines around it. Remember, you don't have to draw these. And then I have H2O. Well, I have 1 oxygen, so that's probably going to be the middle element. The hydrogens go on the outside of that 1 oxygen. So whichever one you have the least of, usually that's the one that goes in the middle. Next step, you're going to draw a single bond to the outside atoms. So a line to the outside atoms. And that line is representing 2 electrons being shared between 2 atoms. You'll subtract, so we will keep a running total, and you'll just subtract each time that you use a pair of electrons. Okay, we'll fill the octet for the outside atoms. An octet means 8. So right here you see fluorine has 2 from this bond, and then 6 more. These have 8. Hydrogen, however, cannot accommodate any more electrons, and so what you see in this picture is you don't see any extra little dots around hydrogen. As soon as it has a bond, then it's completely done. Don't add anything else to it. And again, you subtract. If there are extra electrons, what you're going to do is first try to place them on the central atom, that's the middle atom. Looks like this. Here's a pair of electrons placed on the center atom. If the center atom does not have an octet, doesn't have 8, then what you're going to try to do is steal electrons from the outside atoms and create either a double bond or a triple bond. So, for example, this one right here would look more like this. And so that each atom would have an octet. That's the goal, to get everything to share so that each has 8 valence electrons. Here are some exceptions. These atoms will not fill their octet because they don't have the orbitals to accommodate them. So they are beryllium, boron, and aluminum. These 3. You have to memorize these 3. And that's what they would look like in a compound. They would not steal. They do not have an octet. So this one only has 6 electrons around it, and that's all it can accommodate. This one right here with beryllium only has 4 electrons, and it's done. And aluminum has 6. And yeah, aluminum can form a covalent bond. Strange, I know. All right. If your central atom has more than 8, electrons from bonds and extra pairs. It's possible, it's called something called an expanded octet. That is an exception to the octet rule, meaning it has expanded its octet, it's gone beyond 8. For example, this one. Here you have 2, 4, 6, 8, plus these two, that's 10 electrons around this one sulfur atom. So it's more than 8, that's 10. There are only certain elements on the periodic table that can do this, and that's if the central atom has the orbitals to accommodate it. They're the nonmetals that are in period 3, that's row 3 of the periodic table, and below. They have empty d orbitals, and so they put electrons in those, and you see these expanded octets. All right. If there is a double bond or a triple bond, you might want to check for something called resonance, and we'll get to that. Yeah, you can't see that. Like that. The double bond actually moves around the molecule. So here it goes with this oxygen, on this one it's with this one, on that one it's that one. Alright, here, this is something important that you do need to write or draw a box and to write this in. Okay. Alright, so you need to know what each thing of the drawing means, I guess you could say. One dot is just one electron. If you have a single line between two atoms, that's representing 2 electrons. So we don't draw 2 dots. You can, but we mostly just put a line in between them to show that they're connected. 2 lines represents 2 bonds of what we call a double bond, and here they're sharing a total of 4 electrons. 3 lines, they're sharing 6 electrons. Really what we're trying to do is give each atom an octet except for hydrogen and those other 3, beryllium, boron, and aluminum. Okay, so here we're going to do our first example. We'll do some with single bonds, so we'll take it a little bit slowly. So we have pH 3. First thing we'll do is figure out the number of atoms that we have for each element and the number of valence electrons. So for phosphorus, we have 1 phosphorus. There's no subscript around the P, so just 1. And each phosphorus is in group 5A, so it has 5 valence electrons. And so 1 times 5 is 5. Okay, and then for hydrogen, we have 3 of them, 3 atoms of hydrogen. Each hydrogen has 1 valence electron. And so 1 times 3 is 3. Okay, we're looking for total number of valence electrons. So we're going to take the 5 from the phosphorus and the 3 from each of them, all of the hydrogen, and add them up. And the total is 8. Okay, next step is to figure out the central atom. Since we only have 1 phosphorus and 3 hydrogens, phosphorus is most likely going to be our central atom, so I'll put it in the middle. And I will put all of the hydrogens outside of the phosphorus. Now I could have chosen to draw it a little bit differently with maybe the hydrogen on the bottom or evenly space them out. It doesn't really matter yet. Just note that all the hydrogen go around the phosphorus. Third step is to draw single bonds to the outside atoms. So 1, 2, 3. Okay, so now each of the atoms have their own single bond. Alright, so we're going to keep a running total. So I'm going to subtract 6 because I've just used 6 electrons. Ooh, let's look at that. How did I just use 6? Well, here's 2 plus these 2 plus these 2. That's a total of 6 valence electrons being used. Okay, so that means, 2 for each bond. That means there's 2 valence electrons left. Let's see what step 4 says. It says, fill the octet for the outside atoms. But hydrogen is full. It can only have 2 electrons. It can only have a single bond, and then it's done. So I'm not going to put those electrons on the hydrogen. Instead, I'm going to put it on the central atom, which is actually step 5. Okay. Now I'm going to check to see that each atom has an octet, with the exception of hydrogen. So let's look at phosphorus. It has 2 here, 2, 4, 6, plus these 2, that's 8. Phosphorus has an octet, It's now more stable by sharing those electrons. Hydrogen can only accommodate 2, so it's also more stable. So -2, that gives me 0 left over. Yes, the octet rule was obeyed. We just talked about that. Okay, number 2, we have CHCl3. So we have 1 carbon. Step 1, figure out the number of valence. Hydrogen and chlorine. So 1 carbon, carbon's in 4A, has 4 valence electrons. Hydrogen is in group 1A, has 1 valence. And then chlorine is in group 7A, there's 3 of them, so 3 times 7 gives me 21. Okay. All right, so then what do? We're going to add them up. And in total, I have 26 valence electrons that I'm going to place around this molecule. Step 2, figure out which one is the central atom. Well, here I have the same amount of carbon as I do hydrogen. That's the one I have the least of. So then I'm going to go to a couple things. One is carbon's written first. The other is I can't put anything around hydrogen because it can only accommodate 1 bond. So we'll put carbon in the middle, and everything else is going to go around carbon. So there's hydrogen, chlorine, chlorine, chlorine. I just put them evenly around it. Next step is to draw single bonds to the outside atoms. Okay. Next step is to fill the octet on the outside atoms. Can't put it around, oh, sorry, here we go, -8. So I have 18 electrons left. I have to put those around that molecule. So let's see, hydrogen can't accommodate any more. So let's put them on chlorine. So 2, 4, 6, put them in pairs. This one gets 2, 4, 6, and this one gets 2, 4, 6, and guess what? That's 18 valence electrons, leaving me with 0. Is the octet rule obeyed? Well, let's check. Hydrogen can't have an octet, so it has 2. Carbon has 2, 4, 6, and 8, so that's an octet for carbon. Chlorine has these 2, 4, 6, 8. Same thing for these. 2, 4, 6, 8, 2, 4, 6, 8. The octet rule has been obeyed for the ones that can obey it. Okay. Next example is bromine. We have 2 bromines, so 2 times 7, that's 14 in total. And since there's just 2 bromines, we'll draw 1 bromine as a central atom and the other one as the outside. Next step is to draw a single bond, so that takes care of 2 more electrons, leaving us with 12. So each one of these can accommodate 6 more electrons, 6, 6. That gives us all 12 being used. So that leaves us with 0 electrons left over. Then we'll check to see if the octet rule is being obeyed. Bromine has 2, 4, 6, 8, and so does this bromine. Okay, what about those double bonds and triple bonds I was telling you about? Well, here's an example where it's going to involve multiple bonds, CO2. So here we go. Carbon and oxygen, 1 carbon and 2 oxygens. Altogether, that is 16 electrons we're going to use. CO2, well, carbon's got to be in the middle, and then oxygen around it. So I'm just going to put them evenly around it. Next step is to draw a single bond to the outside atoms. That's 2 for this one, 2 for that one. That's 4 electrons that I've used, leaving me with 12 electrons. Okay, so I'm going to fill the outside atoms. That's 6 and 6 more. And now I've used all 12. Okay. Then I need to know, was the octet rule obeyed? Well, oxygen has 6 plus 2, that's 8. This oxygen has 8, but let's check carbon. Carbon only has 4, so that's not okay. The octet rule has not been obeyed. So here's what you're going to do. The rest, well, step 5 says put them on the remaining if you have any remaining, and we don't. If you don't have any remaining, then we need to steal because the octet's not full for carbon, and so no octet on C. Here's what I mean by steal. So we're going to take some of the electrons that oxygen has and force it to share more electrons with carbon. So let's see. We'll try double bonds. I'll take these two and move it into a double bond. So it would look like this. Now we'll check to see that the octet rule has been obeyed. Oxygen has 2, 4, 6, 8. This oxygen, good. This oxygen, still good. This carbon, not done yet. It only has 6 electrons. It needs 2 more. So we're going to steal from the other side and put that there. And so if I do that, I have 2 double bonds around carbon. This has 8, this has 8, and then carbon, by having these 2 double bonds, has 8 valence electrons. So both of them have an octet. So this is my final answer. You might want to put a box around it so you know which one of these is correct if you drew multiple. All right, let's try another one. Go ahead and try to figure out the valence electrons. All right, so we have silicon and sulfur. So if you figured that out to be 10, good job. We'll put silicon in the middle. It's written first. There's really no middle here. But silicon to sulfur, drawing a single bond to sulfur. That's using 2 valence electrons. And then we have 8 left. Okay, so what do we do? There's no central atom. There's just 2 outside atoms. So I'm just going to evenly put, well, let's put 6 on this one. And that gets rid of 6. So that's 2 left over. We'll put on the silicon. Now we'll check. Has the octet rule been obeyed? Nope. Silicon only has 4. So we're going to need to make sulfur share some more. So let's steal these 2. Let's see what that is. Sulfur's good still. Silicon, not yet. It only has 6. So let's steal 2 more. And now what we have is a triple bond between silicon and sulfur. You noticed I kind of just left these electrons here and used those, so I have 2 on the side and 2 on the top. It doesn't really matter. I could have put these 2 on the side, or both of them on the top, or both of them on the bottom, as long as you see that they have a set of electrons and 3 bonds between the 2 atoms. That's okay. So box around that one. Okay, next we're going to do examples involving polyatomic ions. Remember, we're going to add if the polyatomic ion is negative and subtract if the polyatomic ion is positive. Once the structure is complete, what you'll do is you'll put brackets around the polyatomic ion and the charge in the corner. For example, this one is carbonate. So here's our first example, phosphate, PO4 with a 3- charge. So we'll figure out phosphorus and oxygen. There's 4 of them, 6 valence electrons, 24. The only difference here is now we're dealing with something that's charged. And so 3 negative means that it's gained 3 electrons. So we have to worry about that charge. Gained 3 electrons. So we'll add in 3. So that's going to be a total of 32 valence electrons that we're going to move around the atom or molecule. Okay, so the central atom is going to be phosphorus. We have less of those. Oxygen on the outside. We have single bonds to each one of the outside atoms. That's step 2. Nope, step 3. And then we're going to complete the octet for the outside atoms. That's step 4. Oh, we need to count. Now that's -8, leaving me with 24. So now let's put those electrons on the outside. Each one can hold 6 more. 6 times 4 gives me 24 valence electrons. So subtract 24 and I get 0. So we need to know, has the octet rule been obeyed? Let's check. Oxygen, 2, 4, 6, 8. Same for this one, and this one. Then for phosphorus, it has 4 bonds or 8 electrons around it. So yes, the octet rule has been obeyed. Last thing we need to do is put brackets around the phosphate. Don't forget these. It's easy to forget, but don't forget. Anytime you have a polyatomic, you have to put these. And then you just put the charge in the upper right-hand corner. Let's try a positive one. Okay, so we have hydronium, that's H3O+. So we have hydrogen and oxygen, 3 hydrogens, 1 oxygen. Then we have to worry about the charge. This is a positive one, so we're going to add, no, not add, we're going to subtract an electron because positive just means it's lost an electron. So subtract 1 for charge, and you get a total of 8 valence electrons. So we'll put oxygen in the middle still. Hydrogen cannot be a central atom, not ever. Then we'll put single bonds to the outside atoms. So that is using 6 of the 8, leaving us with 2. Next step is to put them on the outside atoms, the extra electrons, but we can't put any on hydrogen, so it's done. So then the next step, number 5, is to put the remaining electrons on the central atom. So here we go. And then we'll subtract those 2, leaving us with 0 left over. Question, is the octet rule been obeyed? Well, hydrogen can't follow the octet rule, but oxygen sure did. It has 6 here plus those 2, that's 8. Last step, brackets, charge. And that is finally the end to part 1 of Lewis structures. We'll do part 2 tomorrow.